We're delighted to have Lenny Susskind, who's going to be telling us some thoughts about holography and de Sitter space.
I think the official title was some half-baked thoughts.
Well, I leave such elaborations to the speaker.
Right.
You can share again.
All right, let me explain why the title, what I meant when I said half-baked. In fact, let me just go on a rant, an old man's rant. Let's begin with a night thought. In fact, let's imagine a group of very smart theorists who know all about quantum mechanics and relativity, but had never heard about modern astronomy or particle physics. If they were anything like us, they would eventually discover black holes, quantum field theory, string theory, supersymmetry, the holographic principle, large N matrix theory, ADS-CFT. In other words, from the pure theory point of view, they would be about where we are now. What would they take away from all of this? Here's what I think they would say. I think they would say, first of all, if you want to put gravity and quantum mechanics together, you better have a frozen time-like boundary to anchor the theory and to define observables. ADS is great in this respect, and maybe flat space is okay. To make the string scale much smaller than the cosmic radius, and in this case, the cosmic radius would be the ADS scale, the boundary theory better be super strongly coupled. But knowing as much as we do, they might believe that the only theories that can be pushed to super strong coupling are supersymmetric. That would also fit what they know with what they know about matrix theory, where without supersymmetry, you can't even separate two particles. Asymptotic boundaries, super strong coupling, supersymmetry, these would be their touchstones. What would happen then if some crazy man showed up and told them that he had seen the data and could assure them that space has no boundary, that space-time is more like de Sitter space than anti-de Sitter space, that there's no supersymmetry, and despite that, locality works down to ultra-microscopic scales? I'll tell you what I think they would say. I think they would say, baloney, your model is in the swampland. They say this not because of some made-up swampland bound on the inflaton, but because the model violates the entire foundation of their mathematical understanding. Okay, what should we take away from this parable? The answer is I don't really know. I don't think we should stop thinking about ADS and related things. It's obvious that there's still much more to learn. We should continue, but constantly keep in mind that we're missing some very big piece of the puzzle, and not to be afraid to discuss the limits of what we've learned. Personally, I've been thinking about de Sitter space, but to tell you the truth, I don't really believe in the project. I have real doubts that eternal stable de Sitter space, absolutely stable de Sitter space exists mathematically. But even if it does, it's not a good and reasonable starting point for cosmology. It's a theory of Boltzmann fluctuations, and I'll talk about that a little bit. And as I explained years ago, that's not a good place to start for cosmology. I personally think something like eternal inflation, a vast landscape, including terminal vacua, and something that I once called a fractal flow is much closer to being the right thing than eternal de Sitter space. But that's a very, very big piece to try to bite off all at once. So for today, we're just going to talk about just a little bit about de Sitter space and some aspects that, just a couple of aspects that I've been personally interested in because at least at one time, I thought they might really be a no-go situation for de Sitter space. Okay, let me share my screen. You won't see me once I share my screen because my iPad doesn't permit it. So here we go. Screen sharing, screen. Start broadcast. No, I seem to, what happened here? Start broadcast. Can you see my screen?
Yes.
Can you see my screen?
Yes.
All right. So the question I really want to address is, does the holographic principle apply to de Sitter space? Hold on, let me move my apparatus here a little bit, so it's easier for me to deal with. Yeah, does the holographic principle apply to de Sitter space, and if so, in what form? Here are a few papers that address some of the questions that I'll talk about. But the first thing I want to talk about is what I mean by the holographic principle. And what I mean is essentially what the holographic principle first meant. You have a region of space. A region of space means space across time, and it has a boundary. There's a bulk inside it, a time-like boundary, in fact. There's a bulk inside it. It's described by all the various things that we describe bulks in terms of: gravity, metric, action, Einstein-Hilbert action, Newtonian gravity it contains black holes, Hawking radiation, all the things that we think should exist in the bulk. On the other side of the divide is the holographic theory, or the hologram, we can call it. Again, time-like spatial boundary, and on that time-like spatial boundary, there's a theory of some sort, which is purely quantum mechanical. It has a Hilbert space, it has unitarity, it has a Hamiltonian, it has things like entanglement, complexity, but it does not have gravity, at least not in its formulation. It doesn't contain gravity. Assumption of the holographic principle is that the right side can describe everything that's on the left side. Some examples that are very familiar to us: matrix mechanics, matrix theory, which is a pure theory of the quantum mechanics of matrices. On the right-hand side is 11-dimensional supergravity. Conformal field theory, ADS. SYK, JT gravity, and so forth. I wish I could say there were a lot more, but I don't know very many more. And notice the divide is a sharp divide between what is on one side gravitational bulk physics, on the other side pure quantum mechanics. Okay, before I get into what I actually want to talk about, let me just say, in one particular situation, one particular type of theory, which is called DSCFT, I want to explain which side of the divide this falls on. Is it a holographic theory? Is it a bulk theory? So let me just remind you very, very quickly, at least this is the description that Juan gave us. We have de Sitter space, and we make some cutoff at a very late time. Well, it doesn't have to be a very late time, a late time, and we describe the Wheeler-DeWitt wave function on that cutoff surface by a conformal field theory. The partition function of a conformal field theory involving a set of operators A, those could be, we think of those as matter fields, a metric on the slice, not a bulk metric, but a metric on the slice that we slice off, and we construct parametrically in terms of the coupling, in terms of the metric Gij, we construct a Wheeler-DeWitt wave function. If we want to calculate anything from that Wheeler-DeWitt wave function, we have to square it and insert an operator of some sort. And that inevitably means, in the end of the day, we'll be doing an integral over G, over the metric. The whole thing will have the look of a Euclidean quantum gravity problem with matter on a space-like D-1 sphere. I'm going to say this is not a holographic theory, not in the sense in which I said it. It may be very powerful, extremely useful. Certainly in the hands of Juan, it was very useful in studying features of inflation. But it is not what I mean. It's at best a hybrid of some kind of boundary theory and some kind of bulk theory. So I will not be speaking about this kind of theory. What is our best bet for a truly holographic theory of de Sitter space? And the only alternative that I know is to have a holographic theory associated with each static patch. Or maybe it's each pair of static patches. So the first question I want to address, one question, is everybody still there? I've had this habit of losing audiences and going on and on talking to myself. Okay.
Yeah.
Yes, at least some people. I don't mind if everybody leaves their mic open, but at least some people leave their mic open. And every so often when I become insecure, I will say, okay, did you hear that? Please answer me. Okay, first question is, where is the hologram? Now, when I say where is the hologram, I mean the same sense as we say the hologram for ADS is on the boundary. Next, what does the theory compute? In other words, what is the theory about? What do we know about the properties of a holographic description of a static patch? And finally, I want to talk about implementing the symmetries. Now, I may not get to all of this. I'll get to as much as I can. The symmetries that I'm talking about, incidentally, are very special symmetries for de Sitter space. They take one static patch into another. Here I have, this is a picture of two, this is not the true Penrose diagram. It's a doubled Penrose diagram, but that's not important. Here's the static patch associated with a particular, I don't know, we can call him a observer. And here's another static patch. And there must be transformations between these. Transformations between different static patches and also transformations which preserve the static patches are the symmetry of de Sitter space. We would recognize de Sitter space by implementing these particular symmetries. These symmetries are very difficult to implement. No, it's worse than that. They are impossible to implement. But we'll come to it. That's one of the things I want to talk about. Okay. All static patches are equivalent. That's at least in classical de Sitter space. They have a metric. Here's the metric. F of R is, I understand this thing called F of R is called an emblackening factor. I didn't know that. The emblackening factor is universal. The parameter R is the Hubble radius, the cosmological radius of the space. And if we are in a static patch, then what we see is, first of all, the center of the static patch, that's little r equals 0. I'll give that a name. I'll call it the pode. Why I call it the pode? Well, I just like the word pode. The horizon at r equals capital R, that's the boundary out here, and anybody inside the static patch looks out and sees the horizon, a kind of inside-out version of a black hole. Okay, now let's go to a Penrose diagram, a true Penrose diagram of the same situation. What we find when we draw a Penrose diagram is that static patches come in pairs. They come in pairs, which, if our experience with ADS is any guide at all, those two pairs would be expected to be entangled, entangled pairs of static patches. One of them I've called the pode, and of course the other one is the antipode. And they just mean the opposite ends of the boundaries of the boundary, the pode and antipode boundary of the diagram are not true boundaries of de Sitter space. They're points. We'll come back to it in a moment. Okay, so what am I going to assume? I'm going to assume, or I'm going to try to assume, try to explore the possibility that the holographic description of the static patch, or of the pair of static patches, involves a Hilbert space, which is a left cross right Hilbert space, the left patch and the right patch, that there's a Hamiltonian. The Hamiltonian that I'm going to think about is the boost Hamiltonian, the Hamiltonian which slides, which doesn't push everybody upward, but pushes us upward, let us say, on the antipode side and downward on the pode side. And it takes the form of some h right minus h left. As I said, none of this can I prove. All of this is something I wish to explore. From the look of the diagram, you might expect that the state of the system is the thermal field double, as it would be in de Sitter space, as in the eternal black hole of de Sitter space. And the temperature, and this is a peculiar feature of de Sitter space, it's an uncomfortable feature, I think, that if it did have such a holographic description in terms of a Hamiltonian, there is only one allowable temperature. I think what that means is there's only one allowable temperature in which the symmetries of de Sitter space would be manifest or would be true. Okay, the temperature is 1 over 2 pi r, r being the Hubble radius, and the Hamiltonian, the boost Hamiltonian, annihilates the thermal field double state. These are all, as I said, assumptions. Everybody still with me?
Yes.
Yes.
Okay, now let's look at this. Penrose diagram for a moment. Just looking at the Penrose diagram, you couldn't tell, is this the ADS eternal black hole, or is this the de Sitter space that we're after? The Penrose diagrams are the same. However, the geometries are very different. In particular, a slice through t equals 0 here would look completely different. The ADS, the two-sided ADS geometry would look like a wormhole, which expanded out to infinite boundaries on either side, whereas the de Sitter space, the same Penrose diagram or the same slice would look like a sphere with a pode at one end and the antipode at the other end. So they're quite different. And to represent that difference, let's add some structure to the Penrose diagram. Structure that Busso introduced, which are these wedges. First of all, we can label the sides of the diagram by the radii of the spheres at those points. And we see that ADS and DS are essentially exactly the opposite from each other. I'll let you stare at that for a moment. You all know a great deal about it. Okay, what are these wedges? These wedges, for our purposes now, the wedges just tell us whether when we move in the direction outward or move from the direction of the point here, that tells us that the local two spheres are expanding as we move out. And as we move along the tail feathers here of the little arrows, the radii of the two spheres decrease. That's all we need to know really about the Busso wedges here. And notice that they are exactly the opposite in the ADS two-sided black hole and in de Sitter space. Okay, now I want to answer the question, where is the hologram? Where are the degrees of freedom? Where shall we locate them, at least nominally? So let's come first to ADS. And let's take a pair of what Busso would call screens. I'm not sure he'd call them screens, but two surfaces, one over here and one over here. We could work with just one of them. And according to Busso's rule, the entropy found on a segment of a slice here, this pink segment of the slice there, that entropy is bounded by the areas of these, of the spheres at the tips of these Busso wedges. Well, that means in this case here that the number of degrees of freedom, the maximum entropy on this slice here, if these 2 points are very close to the horizon, is just barely big enough to describe the entropy of the black hole itself. It is not big enough to describe all the things that could happen out beyond the horizon. What we do, of course, in ADS is move outward. We go outward toward the boundary, put our screens there, and according to Busso's rule, the entropy on the entire slice, or almost the entire slice, is bounded by the areas of the spheres way out here. If we take those points out to the boundary, we have enough entropy or enough degrees of freedom to describe everything on a space-like surface. And that's why we put the ADS hologram at the boundary. But now let's look at the de Sitter space. Imagine we put our screen over here, and then according to the rule is that the entropy on this little piece over here, this little pink piece over here, is no bigger than the area of the sphere at that point, but the sphere at that point has a small area. It's over here, right over here. The area at that point is small and shrinks as we go to the pole or the antipode. And so by putting our screen out near the pole and the antipode, that's nowhere near big enough to describe all the physics that would happen in the entire static patch. Instead, we're required to put the screen, I keep doing that, the screen very close to the horizon. If we put the screen very close to the horizon, then according to Busso's rule, there's enough degrees of freedom near the horizon here to account for everything that can happen on the entire static patch. So the lesson, the de Sitter hologram, or at least the hologram describing the static patch of de Sitter space, is at the horizon, as opposed to anywhere else. We can probably useful to think of it as a stretched horizon slightly away from the actual mathematical horizon, and for the usual reasons. Okay, everybody with me? Any questions?
Are you going to discuss back reaction?
Back reaction of what?
Of the excitations, of the matter excitations in the space-time. I'm just referring to the fact that in ADS, near the boundary, that becomes arbitrarily small, whereas in de Sitter.
Yes, that's a very big difference. The boundary of ADS is what I would call cold. It's cold because the energy scales to excite it are so high, whereas the horizon is not cold. So this is a big difference. And what we're to make out of that difference, well, I'll talk about it a little bit, but I don't claim to fully understand it. In any case, what kind of degrees of freedom, what kind of theory might we place on the horizon? Should it be a quantum field theory? Should it be a quantum field theory whose degrees of freedom are located on the horizon? And the answer, I think, is no. The reason is that the de Sitter space horizon, or the de Sitter space itself, is a fast scrambler. I'll remind you what a fast scrambler means is that if you drop an object into the toward the horizon, that its degrees of freedom mix up with the entire horizon in a time called the scrambling time. A fast scrambler is one which scrambles fast, and fast means logarithmically fast. All right, so you can do this problem in a baby form in de Sitter space. For example, you can drop in a charged particle. This was the first attempt, this was long ago. The first attempts at understanding scrambling were in terms of dropping in charged particles and seeing how their charge spreads over the horizon. That was for black holes. We can do exactly the same thing for de Sitter space. We can drop a charged particle in. We can solve its field and calculate how it's really the normal component of the electric field, which is a substitute for the electric charge, how the electric charge spreads over the horizon. And one finds, very much like in a Schwarzschild black hole, that the time to spread over the horizon is logarithmic in the entropy or logarithmic in the radius of the horizon. It's a fast scrambler. So de Sitter space, like a black hole, is a fast scrambler, and it does not scramble ballistically as it would in a local quantum field theory. That would suggest, well, let me say, yeah, that would suggest that the degrees of freedom are all-to-all k-local degrees of freedom coupled in a manner, let's say, similar to SYK or something like that. We're gonna have to modify that, but this is. Let me not say that suggests the all-to-all couplings. Let me just say that all-to-all couplings are the kind of things which do lead to fast scrambling, or one of the kinds of things that lead to fast scrambling. So the horizon degrees of freedom should definitely not be thought of as a local quantum field theory, but more like a highly non-local all-to-all coupled system. All right, now, just mainly as a foil for talking about things later, I want to introduce a toy model. The toy model isn't a good model. It does not describe decently any kind of anti-de Sitter space, but it's a useful foil for discussing de Sitter space later. First of all, the pode is a point of instability. What I mean by that is that if you had a particle or an object, a galaxy, or whatever it happens to be, which was slightly displaced from the pode, and you allowed it to evolve, it would eventually fall through the horizon. That means it would move away from the pode and fall through the horizon at a distance r, capital R, away from the pode. That's
Any?
the most, yeah.
In that statement, how do you define where the pode is? Is that just a coordinate statement?
It's where I am. Yes, that's absolutely, it's a coordinate. Well, once I pick a pode, I can then look at the motion of an object relative to that pode. I pick a pode, meaning, what does that mean? That means, really what it means is I pick a point in the remote future and in the remote past, and think of the causal patch. I didn't really fully define the causal patch. Raphael, what is the causal patch? Is it the domain of influence of the?
It's what you just said. It's the intersection of the past
Yeah.
and the future of these 2 points.
Right. Yeah. So you pick a pair of points, one in the past, one in the future. You construct the static patch associated with them. Having constructed it, then there's a natural pode which sits at the middle of it, and anything slightly away from that pode, following geodesic trajectories, will fall through the horizon. All right, so it's natural.
I guess.
Yeah.
Can I ask? Sorry.
Go ahead.
Go ahead.
I'm just so mathematically, I think this is a well-defined statement, but non-perturbatively, I don't think you would expect that we can make sense of an infinitely long world line in de Sitter space.
Yeah.
And so it's not clear that there's any operational meaning to that definition, right?
No, I agree with that. I think what we're trying out now is a set of ideas which we may find in the end simply don't work. And I would like to know if we can form a holographic theory of this type. I would not be terribly disappointed if in the end we find out that there are limitations and that this can at best be an approximation. I
had a small comment. This picture you've drawn about the instability, isn't it another way to say that de Sitter is a fast scrambler? Because in a scrambling time, that purple particle disappears behind the horizon.
Right. No, absolutely. That it's a scrambler of any kind, yeah. But no, the motion of that particle relative to the pode is an exponential growth of the, it's a typical exponential growth associated with an instability. And the non-relativistic model, which is most like this, would simply be an upside down potential, the pole sitting at the top. Let me go back a step. If I were to build a simple model of anti-de Sitter space, a model that's simple enough that I could explain it to a small child, I would say it's a sort of container with a potential that pulls stuff toward the center, a gravitational field that pulls stuff toward the center. Anti-de Sitter space is the opposite of de Sitter space, or de Sitter space is the opposite of anti-de Sitter space in this respect. It looks like a cavity with a repulsive center and an instability for objects located at the top of the potential here. Anything at the top of the potential, if you displace it a little bit, will fall and will fall down to the minimum. I also want to imagine that there are non-relativistic particles, and these particles have been put in with some energy, some temperature, and that they sit down at the bottom here and form a kind of thermal gas with an entropy of order the number of particles. This region is the horizon. This is the pole. Anything you drop in will fall off and eventually be in the horizon. The horizon degrees of freedom just exist there in boring eternal equilibrium. Very boring, but with occasional interesting Boltzmann fluctuations. By a Boltzmann fluctuation, I mean a large-scale fluctuation in which a significant number of degrees of freedom might find themselves up near the pole or someplace else. It doesn't have to be at the pole, but a pole is a convenient place to think about. That's about all that can happen. Well, it's not all that can happen, but this is one of the things that in principle can happen. And of course, it happens very infrequently, but this is all that happens in a pure de Sitter space or in a pure model like this, occasional fluctuations. And it is my belief that what an ideal de Sitter space is or a theory of an ideal de Sitter space is it's just the theory of these fluctuations. But the fluctuations can be interesting. They're very intermittent. They don't take place very often, but they can be interesting. Sometimes people call them Boltzmann brains. Okay, the questions that I want to address is how do you calculate the probability for these fluctuations? How do you calculate the probability for these fluctuations? And I'm going to give you three formulas for the probability of a fluctuation. One is you calculate the entropy of the system constrained to have the Boltzmann fluctuation present. I'm calling the Boltzmann fluctuation theta. Theta or O, I can't remember, theta. Constrained subject to the condition that the Boltzmann fluctuation is present, calculate the entropy of the system. The difference between that entropy and the entropy of the pure de Sitter space, or the entropy without the Boltzmann fluctuation, that is called delta S. And the probability for the fluctuation is just e to the minus delta S. That's one of Boltzmann's formulas. Another formula is that it's e to the minus beta times the energy of the fluctuation. Those two are consistent for an isolated system. And the last formula is, let's suppose that we can quantum mechanically construct a projection operator that projects out states in which this theta object is present. Then the trace of rho times pi of theta is the probability that theta is present. All three of these are the same, basically the same formula, where rho is, of course, just the thermal ensemble. All right, now there is much, this is one thing that you could calculate. How likely is it that, that such a fluctuation exists? There's many other things you could calculate of a more dynamical character. For example, the transition probability that if you start with theta, you end up with theta prime up on the top. Theta prime could exist, could be a slightly different state, or it could have an extra particle falling down in, or whatever. Can we calculate that transition probability? Well, in principle, yes. If we knew what these projection operators were, this is pi of theta, this is pi of theta prime. We can time, if we know the Hamiltonian, we can time translate pi of theta prime, and we can calculate the trace of rho times the correlation function of pi of theta with pi of theta prime. And that's basically the transition probability to go from here to here. So the point is, thermal equilibrium, if you could calculate everything that thermal equilibrium entails, everything possible in thermal equilibrium, there's a lot of stuff there. There's an entire description of evolutions of galaxies, evolution of, it's not totally boring, but the time interval between interesting things happening is very long. All right, so calculating delta S, this is a challenge. How to calculate delta S. In the toy model here, you can estimate delta S. It's basically just the entropy of S itself, of theta itself, is the way to think about it. If a bunch of degrees of freedom separate themselves from the mess down at the horizon here, then the horizon has fewer degrees of freedom. Instead of having n, it has n minus little n, and the entropy of the horizon is diminished by a factor n minus little n. Let's keep it simple. Let's just suppose that the object up here also has entropy of order little n, but much smaller than the coefficient n here. That is something that you'd expect. All right, then you'll find that the delta S for creating a fluctuation up here is just of order n, the number of particles that come up here. Or the number, or just the entropy of the object theta up on the top. And it would say the probability of forming such a fluctuation would just be of order e to the minus some constant times the entropy of the system up here. Little s stands for the entropy of the system up here. So keep that in mind, that for simple non-relativistic models, delta S would just be proportional, roughly of order, the entropy of the thing that appeared that we're searching for up on the top of the pode. All right, now this is not to be trusted.
Sorry, question. Did you say little c is much smaller than 1?
Yeah,
is little c much smaller?
It is typically smaller than 1, where no, not in this formula. Sorry, not in this formula. In comparing the n here and the n here, I would say this c is less than 1. And the reason is simple. The particles that exist up here, if they were found down at the bottom, they would have a fairly large volume to move around in. If they're constrained to be up on the top, they have a smaller volume to move around in. And so the entropy of a group of particles stuck up near the top here would be likely less than the entropy if they were allowed to fall back down into the mush. Okay, this is not terribly important because this is not a good model.
Lenny?
Yeah.
I'm a little confused by the statement about the entropy of the matter that you're making. So
yeah,
the horizon entropy will decrease by an amount that's basically just given by the area decrease of the horizon.
Oh,
right?
This is, now we're doing the toy model. This is the toy model. It doesn't know anything about general relativity.
I thought that the big N minus small n was supposed to capture that. I thought that was supposed to capture some sort of shrinking of the horizon. Is that not?
That is true. That's what we're going to do next. But
But
for the
it
time being,
doesn't capture it accurately,
that's right.
Raphael.
It doesn't capture it correctly. So Tom
Okay,
is
then
right.
I'll hold off asking anything
Oh.
until you're, yeah, good.
By the way, I don't know if I mentioned in the beginning, I think I did, but a lot of what I'm talking about now is very closely connected to concepts that Tom and his collaborators have discussed. And so, good. Okay, so let me move on. Yes, no, what Raphael is saying is correct, but it's jumping ahead of the game here. Now I want to make that jump and say, let's calculate, let's see if we can calculate using general relativity what delta S is here. Okay, so let's calculate using general relativity what delta S is. And to do that, well, first of all, we start with the metric of the de Sitter space by itself and calculate its horizon is R equals big R. Its entropy is pi big R squared over G in 4 dimensions. And that's the initial entropy. Now we consider a system theta and let it be a black hole. Let's think of it as a black hole. For simplicity, let's just take it to be a black hole. A black hole sitting at the center at the pole. What is the entropy of the system? Now, I don't mean the entropy of the black hole. I mean the entropy of the whole system, including the black hole and whatever else happens to the rest of the system. And for that, all we need to do is take the metric of the de Sitter space, including with its black hole. This is all you have to do to get the entropy of the black hole in de Sitter space is to add a Schwarzschild 2mg over r inside the emblackening factor. Then recalculate, sorry, hold on. Recalculate the area. We can recalculate the area of the horizon. The horizon is defined by setting the emblackening factor equal to 0. We find epsilon here, the decrease in the radius is just mg. And what do we find? We find that the entropy of the system that now contains theta, this is not the entropy of theta, it's the entropy of the system which contains theta and other stuff, is just pi g times r minus mg squared. And the deviation of the entropy from the original de Sitter entropy is just 2 pi mr. That's just this product, pi over g, r times mg. That's just 2 pi m times r. The g's cancel. And that's it. So this is the probability of nucleating, or whatever it is, or what do we call it, nucleating a black hole of mass m. Big R here is not the Schwarzschild radius of the, if this were the Schwarzschild radius of the black hole, this whole thing would just be the entropy of the black hole. This is not the Schwarzschild radius of the black hole. This is the cosmic radius of the horizon. Okay, so we have succeeded in calculating it. And of course, we can use that to calculate the probability. Now, Boltzmann tells us something else. Boltzmann also tells us that the probability for theta is e to the minus m divided by the temperature. This is just the Boltzmann factor for an object of mass m. And so thermodynamics basically tells us that m over t must be 2 pi mr. We knew this anyway, in fact, but let me just say it this way, that the consistency of thermodynamics with fluctuations tells us that m over t must be 2 pi mr, and it tells us the temperature of the de Sitter space. I emphasize this because it's a way of thinking about de Sitter space thermodynamics, which doesn't require us, for example, to change the cosmological constant, which doesn't require us to think about variations of things that we may not be able to vary. Instead of thinking about how things respond to changes in cosmological constants and things like that, you think about how energy is partitioned between fluctuations and the rest of the system. And that gives you another form of thermodynamics, which in this case just tells you that the temperature is 1/2πr, and that's correct. That's
Sorry,
consistent.
could I ask a question here?
Yeah.
It's a naive question. It looked like you dropped the term proportional to m squared.
Yes, I did, because it's much smaller.
Does that mean that there should be a correction to the formula for T?
Yeah. Plus order m squared g squared. But you know, that's
then the m's don't cancel when you set the two things equal. So what's
that's very small. That's extremely small by comparison with this big thing here. How big is the quadratic term here? Is the entropy of the black hole itself, m squared g squared pi over g. That is equal to, let me write it another way. It is equal, all right, it's equal to the same thing that I've written here, except substituting the Schwarzschild radius of the black hole. So the Schwarzschild radius of the black hole is 1 kilometer. The radius here that goes into this formula here is 10 to the 10th light years. So the m squared g squared term is entirely negligible. And that's the whole point here. The whole point here is that something has given us an answer which involves a much bigger exponent here than you would have gotten by just using the entropy of the black hole itself. I don't know if that answers the question or not.
Sure. Well, why couldn't you make the black hole big?
Oh, you can. No, you can. You can. I should have said that I'm going to think about a small fluctuation. I'm working to first order in the, yeah, you can think of a black hole whose entropy is as big as 1/3 the entropy of the.
I think it's worth pointing out here that our usual way of understanding the temperature of de Sitter space is by thinking of small quantum field theory fluctuations around the de Sitter space. So by definition, we only really know that de Sitter space has an exactly thermal formula for small fluctuations around the vacuum.
That may be.
That's all we know. That's from the Gibbons-Hawking derivation. That's all we know.
Yeah. Okay.
I think another important point, though, is that, well, you're focusing on the production of small black holes by fluctuations. Yeah. But for small enough m, those are not the dominant things that will be fluctuating. And the correction to the Boltzmann formula will be more important than m squared for more extensive objects, like you could fluctuate some radiation.
Oh, I see. But it's going to definitely be small compared to this.
Well, this is a kind of Bekenstein bound, which yeah, it's not going to exceed this, but it could saturate it, for example.
A small black hole?
No.
No.
For radiation.
But if you radiate one Hawking particle of the typical de Sitter temperature, that has of order this entropy, namely 1.
It has an entropy of order 1.
Yeah. Right.
Yeah, which is the same as delta S.
M?
Yeah.
In that case, m is 1/r.
If the fluctuation is small enough, then its own entropy competes with this formula. That is correct.
Let's say that again now. I didn't understand that. This is a big number.
If m goes like 1/r, then this is
delta
S
like
is
1/r. If m goes like 1/r?
Yeah.
Oh, that's really small.
Yes, indeed. And it's something that can't be localized really on the code.
I see. I understand your point. Okay.
But m could be 1,000/r, right? So there's just a big regime where you're not making black holes, but you are fluctuating stuff.
Yeah. Yeah, no, that's correct. But those things all have wavelengths, which are, it's not cosmological, at least astronomical. But I understand what you're saying. So let's just restrict ourselves to black holes of mass much bigger than the inverse of R. In other words, black holes of ordinary black holes. Okay, so good. Now I want to come to another formula, a distinct formula for delta S, for the probability for nucleating such a thing. Let's start with delta S equals 2 pi mr. Okay, and let's calculate R. First of all, pi r squared over g, that's this formula over here, is equal to the S naught means the entropy of the de Sitter space. Naught simply means de Sitter space. Pi r squared over g is equal to S naught. So from that I can compute R. On the other, same type of formula over here for the entropy of the black hole, it's 4 pi m squared g, and that'll tell me what m is over here. I multiply those two together, and here is what you get. You get that the delta S, the thing that goes into the Boltzmann formula and the exponent, is the square root of S naught, that's the de Sitter entropy, and the black hole entropy. A curious formula. And I claim that that kind of formula has all kinds of hints in it about what the fundamental, what the holographic degrees of freedom are. Tom knows this very well, and I'll just repeat the story here. I want to compare this formula here, which contains only entropies of the various constituents. The horizon, S naught is the original entropy of the horizon, S, little s, is the entropy of the black hole. Let's compare that with the toy model, first of all. The toy model says that the fluctuation, or that the delta S in the toy model, is just of order little s. The delta S that we compute is much, much bigger than that. So it means that compared with the toy model, it's much, much harder to fluctuate a object of mass m than it would be. It's much harder in the de Sitter space, much less probable. And one question is, what is the reason why it's so much less probable? So I'm going to describe now a model which was discussed by Banks, Fiol, and do I have this right, Tom? Tom, are you there?
Yeah, that's right.
Yeah, I also discussed it somewhat later. Tom and I discussed it. I can't remember how long ago in ancient histories. I remember sitting in a cafe someplace in some foreign country. I don't know where it was, discussing these kind of things. Maybe even before. No, it wasn't before. It was not before this, but it was before this. Banks and Fischler had a follow-up paper on it. And I'm going to discuss their understanding and my understanding of this formula over here.
Lenny,
okay,
I'm so sorry, but
yeah.
Can I ask one more time? I don't understand the significance or the legitimacy, I guess, of why you're restricting to black holes in the fluctuations that you consider. So even if I don't allow you a mass that's less than, even if we restrict to m being greater than the Planck mass, which I think physically there's no particular reason to, but let's do that. Then still for small enough m and sufficiently small cosmological constant, the fluctuations are not going to be dominated by the production of small black holes. There's just more entropy, there's more phase space in the production of lighter particles, gases of lighter particles. And the statement, the key statement that you're making about the relation between these entropies is not the case, doesn't hold in that regime. This geometric mean formula.
Okay, so where does it hold?
It doesn't hold for exactly the same reason that it wouldn't hold for an
No,
ordinary heat bath.
where does it begin to hold? How massive do you have to be when it starts to hold?
I think you really have to restrict to black holes for that formula to be correct.
That's what I was doing.
Yeah, that's why I'm asking, what is the significance of that? I mean, it seems to me that black holes, since they don't dominate the thermal ensemble at low energies,
But at some energy they do. There's some energies they do, isn't that right?
Yeah, Raphael, if you take any ordinary particle mass and put it into that formula, not a massless particle with frequency that's, I mean, wavelength that's, you know, a few decades less than the cosmological horizon, this formula is still correct. If you
There's
put
clearly
in
some limit you can take in which is correct, but the limit that I would like to discuss for a moment is one where we take the mass to be fixed. It could be bigger than the Planck mass, and we take the cosmological constant to 0. In that limit, you would not be dominated by small black holes, and this formula would not be correct. And so I'm trying to understand why that's not the right limit to think about.
Well,
but this formula for the entropy is true even if the object is not a black hole, because the field,
true,
the gravitational field of a massive object far from the object always looks like the Schwarzschild field.
The formula I'm referring to is the one in which the entropy of the object that's being fluctuated, and the little s is the entropy of the black hole, right?
Yeah, that's correct.
If I take that to be the entropy of the object that's being fluctuated more generally, then this formula is not true, I think.
Oh, I think that's correct. No, I'm sure that's correct. This is specific for black holes, absolutely.
Now, the formula that is correct, though, is square root of S0 times the mass of the object.
Something like that. Well, that can't be dimensionally correct, but
yeah, the mass in Planck units.
The mass in Planck units. That's right.
Yeah. But permit me the luxury of just thinking about black holes for the moment, and we can come back to that. Okay, so how do these models work? I would call these toy models with strings attached. Instead of just having n non-relativistic particles, we have n, I guess we could call them d0 brains, but they're objects which strings can attach to. Another way of saying it is we're talking about matrix models. Mij is the string field operator, the creation and annihilation operators that create and annihilate strings connecting I to J. These are familiar things from matrix theory and other situations. And we have a degree of freedom like this for every pair of n constituent or n d0 brains. I'm just representing that by drawing a collection. The black here are the d0 brains, and the blue are not necessarily strings. The blue represent the modes. They represent the matrices Mij. They may or may not be occupied by having strings excited. Typically in thermal equilibrium at a temperature, the kind of temperatures we want to think about, the strings would be excited, and so in the horizon degrees of freedom, and so we would expect a big soup of strings and d0 brains, with on the average some number of strings connecting every pair of d0 brains. That's a model. That's a model for the physics here, and the degrees of freedom are these Mijs, and very similar to what we do in matrix theory. How many Mijs are there? There are order n squared of them. And so we would expect that this system in thermal equilibrium above some very low temperature would have an entropy of order n squared. In this case, not n, but n squared. What would we mean by a Boltzmann fluctuation? Well, in the model, the idea is that a Boltzmann fluctuation is what happens when a group of particles disconnects itself completely from the rest of the horizon degrees of freedom. I won't try to justify that. It seems like a reasonable, and certainly it's the kind of thing one expects from matrix theory. when this disentangles itself and disentangling itself, first of all, may say something about entanglement, but I also just mean that the string modes which connect the two lumps here are in their ground state. That's the way we might describe a Boltzmann fluctuation. And that Boltzmann fluctuation will have an entropy of order little n squared degrees of freedom. Okay, so what's the difference between the original entropy of the starting horizon and the horizon plus little fluctuation? Well, it contains a term n minus little n. That's the remaining number of the zero branes in the horizon degrees of freedom squared plus order little n squared. In other words, it will be proportional to big N times little n. But big N times little n is nothing but the square root of S naught times S.
This formula with the S naught and square root of S naught times S, that's special to 4 dimensions, right?
You betcha. That's correct. That is correct. And we're going to talk about that.
Okay.
We're going to talk about that, I don't have a wonderful story to tell about that, but I do have a little bit of a story to tell about it, which is kind of interesting. So, all right. So another way of thinking about it then is that delta S is simply the cost of freezing the by off diagonal. I mean the strings freezing out, or saying there are no strings connecting theta with the horizon. In other words, it's the cost, if you like, of just cutting them. I don't know, cutting them is not the right way. Constraining them to not be there, the strings not be there. I'll call it the string freezing factor. This type of factor, and I'll refer to this effect as the string freezing effect. And what it's saying is, if you want to reproduce the kind of entropy for fluctuations in de Sitter space, there's something going on which requires you to cut the connection between the degrees of freedom of the black hole and the horizon degrees of freedom. Okay, now somebody, I believe it was Juan, asked me about higher dimensions. So let's see what we can say about higher dimensions. It would be lovely and nice if the story just persisted for higher dimensions. As we'll see, it does not. Okay. To go to higher dimensions, we do the same thing. We take the emblackening factor. Now the emblackening factor is the same for pure de Sitter space, but if there's a mass, this is not M, this is mu over here, where mu is equal to this object. This is a general formula in little d dimensions. Don't worry about it. Don't try to memorize it in the next 10 seconds. You'll fail. Well, I don't know, maybe you won't. And the horizon, of course, is just a place where the emblackening factor is 0. If you work it out again to first order in mu, or also to first order in the mass of the little black hole, you'll again get something which is big R minus something proportional to the mass. It now contains in various ways big R. Okay. You can use this to calculate the change in the area due to putting in a mass. And again, if you work it out, you'll find it's exactly equal to m over t. This much doesn't change. It's exactly the Boltzmann factor in every dimension. That had better be, otherwise we'd be making some bad mistake. Delta S, is equal to the mass over t again. But now I want to express this in terms of the entropies of the two objects again. And so we have to go through a rigmarole. It's not too hard. It's pretty easy. Just use some of the equations that I've already written down. And here's the formula that you get. Delta S the string freezing factor contains a numerical factor depending on the dimension here, which is not important for us here, and it contains powers of the entropy of the black hole and the entropy of the de Sitter space. For d equals 4, if I haven't made a mistake, it goes back to the same formula that we had before. But for large d, as d gets larger and larger, it tends towards something which only depends on small s. Notice the exponent for large s goes as 1 over d, and so large s disappears. And what this means is somehow it's much easier at high dimension to disconnect the fluctuating degree of freedom from the horizon degrees of freedom. And the answer is very similar to what we had in this early toy model, just something proportional to small s for large dimensions. In other words, another way to say it is the string freezing effect is much weaker for large dimension. In fact, as we get up to very large dimension, it looks like the string freezing factor goes away altogether. And that's a bit puzzling for the following reason. Well, let's see how we can say this. It looks like the degrees of freedom which connect the fluctuating system to the horizon have become totally unimportant. One might say that, one might worry about that. One might worry that the all-to-all coupling required for fast scrambling disappears at large d. That the degrees of freedom become not so thoroughly interconnected. And you might worry, what happens to fast scrambling under that circumstance? Well, the answer will turn out to be that you don't really need all-to-all coupling to have fast scrambling. You need something that I'll call enough to enough to make fast scrambling. And how much is enough? And is it consistent with this kind of formula? And I'm going to construct now a very crazy model which shows that these things are consistent, that you can let's say we can reproduce this formula here with a system for which we have good reason continues to be a fast scrambler. I'll call it the sparse matrix model. And here's how it's defined. Again, you have a collection of D0 branes. The left diagram here represents all of the possible modes that were there in the original model. Namely, every D0 brane can be connected to every other D0 brane by any number of strings. The MIJs are there for all possible pairs of D0 branes. The sparse model is defined as follows. Hold on a second. Yeah. You go through this interaction diagram and you go to each degree of freedom and you either eliminate it or you don't eliminate it probabilistically. The probability being given in a moment. So you start eliminating. Probabilistically, and what are you going to end up with? You're going to end up with a sparse version of the interaction diagram. I will take the probability to not delete. The probability to not delete is some constant divided by n, the number of D0 branes, to a power p. This means that as n gets large, you eliminate a larger and larger fraction of the modes. You eliminate them as possible excitations. The number of surviving modes in the end is C times n squared, yn squared, that's the original number that we started with, divided by n to the p. That's the probability to not eliminate, is C over n to the p. That's the number of surviving modes that are left after this decimation of the system. What is the entropy? The entropy of the pure de Sitter space, that's just capital N to the 2 minus p. Yeah, this is n to the 2 minus p. The number of surviving modes is n to the 2 minus p. We might expect that that's equal to the entropy of these degrees of freedom. What about the theta? What about the small black hole? Well, we do the same thing that we did before. We remove little n degrees of freedom from the horizon soup, and we calculate the remaining entropy, and that will be little n minus big N minus little n, again to the 2 minus p. And we can work that out, and we find that the delta S, the entropy deficit, is capital N to the 2 minus p minus 1 times little n, which we can rewrite in terms of the entropy. Here are the entropies. The entropies are n's raised to powers. And we can rewrite it as S naught to the 2 minus p minus 1. Well, you can read it. I don't need to read it out loud. It looks sort of similar to the formula that we're trying to reproduce. Here's the formula we're trying to reproduce. Again, a little s to a power, a big S to a power, and we can equate these powers. For example, we can equate the power of little s here, that's s to the d minus 3 over d minus 2, to s to the 1 over 2 minus p, and that gives us 2 minus p is equal to d minus 2 over d minus 3. We can do the same thing with big S, and we get another formula. Well, as it turns out, these two formulas are identical. They are not two different formulas. They are the same formula, and they give you the answer that P, this power P in the statistical elimination of modes, turns out to just be d minus 4 over d minus 3. Not a particularly special number. Notice that it goes to 0 at d equals 4. That means that you didn't decimate at all. You didn't cut out any of the degrees of freedom. And it goes to 1 as d goes to infinity. As d goes to infinity, this goes to 1. And so we can ask now, for different d's, in particular for d equals infinity, where my biggest concern is, where it looks like you've decoupled everything, what does the interaction graph look like? In other words, what are you left over with in terms of a graph when you've eliminated string modes according to the probabilistic rule involving this d here? You know?
How about d equals 3, Lenny?
D equals 3 is not a good example. There are no black holes in 3 dimensions. There are no de Sitter black holes in 3 dimensions anyway, I think. There's anti-de Sitter black holes, but there's no de Sitter black holes. There's no flat space black holes.
I thought the 3-dimensional de Sitter black holes. No?
Are there?
Okay,
small black holes? Well, it can't be, because if there were small de Sitter space black holes, then there would be small flat space black holes. So I don't think so.
No, they're not.
Yeah, okay. Okay, so what are the number of surviving edges after you do this decimation? Well, the number was 2 to n to the 2 minus p. It was n squared when we didn't do any decimation. N to the 2 minus p. As d goes to infinity, that just goes to a constant times n. That's the number of remaining modes. Notice that the number of remaining modes did not go to 0 as d went to infinity. It went to n. That's proportional to the number of vertices. So that means the interaction diagram has about as many edges as it does vertices. Somewhat bigger, but only by a numerical constant. The constant c here is called the degree of the graph, and it's simply the number of edges coming out of each vertex on the average. So we have a random graph of average degree 2c. That's the way the graph theory works out. Here's a non-random graph of degree 3. The non-random graph of degree 3 is just a lattice in this case. Excuse me, I just lost my picture. Hold on. It's just a lattice. And if you were to calculate, you keep going until you run out of the zero brains. You keep building it until you run out of the zero brains. This is a very non-random graph. And it has a diameter which grows as n to the 1/2. Diameter means the largest distance between any pair of points. The 1/2 is just because it's in 2 dimensions. It's a power law in n, the way the diameter of the graph grows. Random graph of fixed degree or fixed average degree is a different kind of graph. They're called expander graphs. So I'll tell you just a little bit about expander graphs. Here's a picture. It looks like a cabbage. Here's a picture of an expander graph. The reason I drew it with wiggly lines is it turns out the eye much prefers the wiggly lines when looking at these things. I tried drawing it with straight lines and you couldn't decipher anything. The wiggly lines somehow made it more visible. The nodes are the D0 brains. The links tell you which modes you've kept in the system. And these expander graphs, I'll tell you what they look like. They're, first of all, statistically homogeneous. They're everywhere pretty much the same. They're not perfectly homogeneous because you did this by a random selection, but they're statistically homogeneous. And if you start any place at any point and work outward, whoops, excuse me, what you will see is a tree graph. Start at any point and work outward, and on the average, you will see a tree graph, a growing tree graph, which grows exponentially. That's true starting anywheres, although it's only easy to draw starting at one point. And that tells you that the number of nodes increases exponentially. The number of nodes increases exponentially with the distance away from a given node. And it tells you that the diameter of the, until that, of course, stops. You only have a finite number in. I think it stops when you've covered about half the nodes. When you've covered about half the nodes, it stops growing. The diameter of the graph, meaning the largest separation between any pair of points, grows like logarithm of n. That logarithm of n is important. First of all, it would tell you that the diffusion time on this graph, you start something happening somewhere and it diffuses outward, takes a time of order log n, not n to a power, as would be the case for a non-random degree 3 graph. Diffusion time is log n. It's also true that quantum systems on expander graphs, while the expander graphs are vastly sparser than all-to-all couplings, they are much sparser, they are still fast scramblers. I refer to a paper by Susskind, and Swingle, studying fast scramblers on these kind of graphs. And furthermore, expanders are the sparsest fast scramblers. If you make the graph any sparser, in other words, if you make the probability any larger to eliminate edges, you will destroy the fast scrambling property. So that's the situation. Now you look at things, you have d equals 4, d equals 5, d equals 6, up to d equals infinity. D equals infinity is where we're getting these expander graphs. D equals 4, we have all-to-all couplings. And everywhere's in between, they're all fast scramblers. If we went past p equals 1, the fast scrambling would disappear. So it seems this is by way of an existence proof, if you like, that the weakening connectivity implied by the diminishing string freezing effect is consistent with fast scrambling. I was worried about that. I thought the fast scrambling would be destroyed. Okay, let's see. I've gone on a long time, longer than I thought I would. The next topic I was going to take up, all right, Ed, what is the time constraint?
You can go on a bit, not too much more.
No, I'm getting tired myself. Okay, yeah.
For the hardcore, we'll reconvene for discussion when you can explain whatever you haven't had time for. But at least give us a couple highlights of what this would be.
All right, so supposing I give you a fast scrambling quantum system, it could be, and it has some manifest symmetry, some obvious symmetries, but nothing very sophisticated. How can I tell that, excuse me, how can I tell that quantum system represents de Sitter space and not something else? I mean, the systems I've described are very similar to the same systems that I might try to use to describe black holes. How can I tell if it's de Sitter space or something else? And I think the answer is the symmetry of the system, the full symmetry of the system, in particular, the symmetries which relate different static patches. Here again, there's two-dimensional de Sitter space. It has a pair of static patches, green and pink. There are symmetry transformations of the de Sitter space, which move the static patches and take them to new static patches. Those symmetries are a non-compact OD1 group of some sort. And we might ask, is that symmetry realized by the system that I've constructed? If it is, then it has a chance of being de Sitter space. If it's not, well, then it's something else. So the question that I want to raise then is, what do we know about the possibility of being able to implement the symmetries which take us between one static patch and another static patch, or between one pair of static patches and another pair of static patches? Notice that the endpoint of this static patch over here, where is it? Over here is behind the horizon, so to speak, of the original pair of static patches. So we're moving things around, taking things from inside the horizon to outside the horizon. And these are symmetries. These are not symmetries that we would expect for any kind of black hole system. They're new symmetries that de Sitter space has to have. So I would say we recognize de Sitter space if the system implements the symmetry group. Well, all right, I'm gonna stop here. What I'm gonna tell you is, number one, that it is impossible to represent the symmetry group. There's a no-go theorem about it. The no-go theorem is an old no-go theorem from many years ago, but that old no-go theorem also applies to ADS2, and it applies equally well to a system that we've been studying for a number of years now, namely, let's see, where is it? in SYK JT ADS2 system. The same kind of and there we've learned what we've learned is that the symmetry can at best be approximate, but I think it's also true that that symmetry can be, I don't know if it can be exact. One, can the SL2 symmetry of JT gravity be exact in the ensemble average sense?
I'm not sure how to think about the symmetries in the ensemble average way. I mean, they're acting on some Hilbert space, and your old argument applies. So,
Yeah. But there are certain things that can be true. For example, okay.
Yeah, I mean, of course, yeah.
Well, okay, what I will say, if we have a little more time later, is the two situations are very parallel. What happens in de Sitter space and what happens to the anomalous symmetries in the anti-de Sitter space of the SYK model seem to be.
One comment is that the symmetries can be exact in the n to infinity limit of, for example, SYK.
Yes, and also right, and I think right, and I think they can also be exact in the n equals infinity limit or the of de Sitter space, if such a limit exists and makes any sense. But what I think I would suggest is that perhaps the logic of the breaking of the symmetries of de Sitter space is similar to the logic of the breaking of the symmetries of the ADS2 space, and that the upshot, it's just a suggestion, is that de Sitter space is really realized as an ensemble average rather than for individual exact versions of it. But I think I've gone on long enough now. I've certainly gone on long enough for me. I've reached an age now where I can't go for more than an hour without getting tired.
Well,
Okay.
thanks very much for this, Leonard.
Yeah, you're welcome.
Well, shortly we'll adjourn for 10 minutes, and those who want can join for a discussion on the other Zoom link. But maybe before we do that, I'll ask if there's any quick questions anyone wants to ask now.
Well, just one remark. I'm hoping that what I meant by saying something was half-baked is only that it needs some more time in the oven before it becomes fully baked, as opposed to the other idea of half-baked. Okay, so are there any questions?
Yeah, Lenny, I have a question. The constraints in the d equals 4 case, I can think of those as just a constraint on a fixed Hilbert space. There's you have some operators, you have to set those operators equal to 0 on the constraint states. I didn't understand whether your probabilistic constraints had a similar interpretation.
No, right. The probabilistic constraints are not probabilistic in that sense. They're probabilistic in defining what modes exist and don't exist. I'm making up a system. This is a highly artificial thing to do,
Okay,
and its only purpose is to convince myself of an existence proof. So let me just go through. I'm not saying statistically that there are no strings. What I'm saying is statistically there's only a certain subset of the modes allowed that can exist.
Okay, so I should think of the model as a model on this expander graph, period.
Yeah.
Just that.
Yeah.
Okay, that now I understand.
Yeah, and I'm not advocating the expander graph picture of de Sitter space. I simply used it to convince myself that there was no conflict between this formula here, not this, you know which formula I mean.
Yeah, I know exactly.
This one here, and the fast scrambling
Fast
character,
scrambling.
right?
I actually have a comment, which is
Yeah.
that the finitely connected graph, which for you corresponded to d equals infinity, seems like the most natural fast scrambler, because in that case, the logarithmic timescale exists geometrically, whereas in the other
That's
cases,
correct.
you can have much faster scrambling, and to get
That's
logarithmic,
right.
when you adjust the
That-
coupling constant.
Yeah, you have much faster scrambling, but then you readjust it by readjusting the coupling J
Yes.
by dividing by some power of n. I think that's what you're saying.
Yes. So in the other
Yeah.
cases, you adjust the coupling to get the answer you want, but
Yeah.
in the sparse case, in the extreme sparse case of finite connectivity, you
It's
get
more
the
natural.
answer automatically for geometrical
Yeah.
reasons.
Yeah, that's correct.
So definitely,
But yeah,
if that was all we knew, I definitely would have said that was the most natural fast scrambler.
I know what you mean. I know what you mean. And then matrices wouldn't, matrices would not fall into that class. But even the all-to-all couplings still do satisfy the fast scrambling rule that that the scrambling time is beta times log s, because when you rescale the j's, you also rescale the scale of the temperature.
Yes,
So
that's equivalent to saying that they make black holes, or at least they're believed to.
yeah.